Last class we have discussed nuclear fusion. So in this class we will discuss nuclear fusion. So see some applications of nuclear reactor where it uses nuclear fusion uh, process. Okay, so these are the uses of nuclear energy. Okay, so here the first use of nuclear energy. So we can use nuclear energy so in both in nuclear fusion and fusion process. So we are discussing the applications of nuclear fusion process. Okay, so here we can use nuclear energy to generate electricity. Okay, it is used in the process of generation of electric power. This is one application. We have discussed how the electricity will be generated by using nuclear energy. Next, second one, not only electricity, not only used nuclear energy, not only used in producing electricity, but also used and the production of radioisotopes. Okay, so in the fission process, we will get different radioactive elements. Those are also very useful. Okay, so in the medicine, so see some applications of these radioactive isotopes in the field of medicine. See the first isotope, radioiodine, is used in the treatment of thyroid glands. Okay, and radio cobalt is used in the detection and treatment of cancer. This is one of the radioactive isotope. And radio sodium is used to find out how a given medicine is circulated in the human body. Okay, so and the radio phosphorus is used in the treatment of skin cancer. Okay, the end product are also very important in the different fields of science. Okay, this is the second application. So these uses of these radioisotopes in different industry industry and medicine also, these are useful. Okay, so, and third application, third use of nuclear energy. Nuclear energy is also used for driving heavy machines like automobiles, like submarines. Okay, so it require enormous amount of energy to run a submarine. So we use nuclear energy so in submarines. Okay, then the fourth application, the energy used in warfare for creating destructive atomic bombs. So in order to, if you want to make atomic bombs, you can make by using nuclear fission process. Okay, so this is also, so it follows a uncontrolled chain reaction. Nuclear reactor so uses control chain reaction. Atomic bomb, the reaction is uncontrolled chain reaction. So that is also useful in creating destructive atomic bombs. Okay, these are some uses of nuclear energy. Okay, so next, so in this class we will study nuclear fusion process. Okay, the last class we have discussed nuclear fission. What is nuclear fission? In a nuclear fission process, a heavy nucleus splits into two intermediate fragments. Okay, so along with the fragments, neutrons and large amount of energy will be liberated, and we can use that energy to produce electricity. And end product gives us radioisotopes used in industry and medicine. Okay, so these are the different applications already. Just now we have discussed. Now, so nuclear fusion. So what is a nuclear fusion? Here in the nuclear fission process, so here two lighter nuclei, two or more lighter nuclei combine to form a heavier nucleus. Okay, so here, here two lighter nuclei combine to form a heavier nucleus. Okay, so when two lighter nuclei combine together to form a heavier nucleus, what happens to the binding energy? Binding energy increases. Okay, so that will be released in the form of energy. Okay, so once again see the definition, the process in which two or more lighter nuclei combine to form a heavy nucleus with the emission of energy. This is called nuclear fission process. Okay, nuclear fission process is what? The splitting of heavy nucleus into lighter nuclei. That is nuclear fission. What is nuclear fusion? Your lighter nuclei combine to form a heavier nuclei. So opposite, reverse process. Okay. No, and for to ignite nuclear fusion process, so it require a temperature of about 10 power of 7 Kelvin. Okay, it takes place at higher temperatures only. In order to ignite, in order to start nuclear fusion process, we need a large temperature, enormous amount of energy. We need 10 power of 7. We have to maintain 10 power of 7 Kelvin of temperature. Okay, so then only these lighter nuclei combine to give a heavier nuclei. So we'll discuss the reason why this much of temperature is required to fuse two lighter nuclei to form a bigger nuclei. Okay, so I'm going to third point. So here these reactions, nuclear fusion reaction require uh, temperature. That is why these reactions are called thermonuclear reactions. Okay, this type of reactions where the temperature is required to ignite the process, that is called thermonuclear reactions. Okay, so here, nuclear fusion reaction takes place where this nuclear fusion reaction takes place in the sun and other stars. The source of energy of sun and stars is the nuclear fusion, not a fission. Okay, so it produces enormous amount of energy. Okay, continuously. Okay, so next. Uh, Nuclear fusion produces more energy than the fission process. So we have discussed the energy liberated or emitted in the nuclear fission is about 0. Actually, I'm discussing here the conversion of energy. In terms of conversion of energy, here in the fission process, in the nuclear fission process, only around 0.1% of mass will be converted into energy. Okay, just 0.1, just only 0.1 convert percent of energy will be converted. Only this much of energy converts into energy, produces a lot of energy. But in the fusion process, it is about 0.7% of mass will be converted into energy. It produces more energy than the fusion process. Okay, so why? Because conversion of mass is more in the fusion process. Okay, and the next so these are few points, and we'll discuss this process in detail. Please remember these points. So what is a fusion? So two lighter nuclei combine to form a bigger nuclei. That is a fusion process, and it takes place at a very high temperatures. That is why this fusion reaction is known as thermonuclear reactions. And what is the source of sun and other stars? Nuclear fusion. And nuclear fusion produces more energy than fission process. And see the conversion rates here, conversion amount here. In fusion, just 0.1, around 0.1% of mass will be converted into energy. In fusion, around 0.7% of mass will be converted into energy. This is fusion process. Okay, no, so you can see how they are combined here. Two lighter nuclei, hydrogen and hydrogen, one H2 and one H2, two deuterium nuclei combined to produce two helium. Actually, it is helium 23. Helium 23. Actually, one is only three particle will be there here. We have two particles, one proton. Actually, it is one H2. This is one H2, and this is also one H2, one H2, one H2. Two deuterium nuclei combine. Sorry, I'll erase it. Okay, it is not drawn clearly. One H1. This is one H1. Sorry, one H2, one H2. So two protons, one plus one, two protons, one plus one, two protons, two neutrons, one plus one, two protons and two neutrons. Okay, total four, two plus two, four. So here, so it become actually helium 23. So unfortunately, one more particle came here, but at only three particles. One of the neutron will be converted into proton. So This is not exactly correct. So just what happens in the fusion process is presented in the figure. So two lighter nuclei are combining to form a bigger nuclei. So and few particles and energy will be liberated here. This is what happens. Now, what is the reason? What is the source of stars and sun? Stellar and solar energy. Here, stellar so means stars energy and sun energy is due to this nuclear fission process. In the nuclear fission reactions, two types of cycle occur. One is called proton cycle and other is called carbon nitrogen cycle. Okay. So in the sun, mostly this process will take place. Proton cycle takes place. Okay. So so we are not going in the details of this reaction. Just we will discuss what is this reaction, proton cycle, how it takes place, and how this energy will be released. Okay. So in this proton cycle, we'll discuss here. It is a thermonuclear reaction that occur uh, is given by one of the thermonuclear reaction, that is proton cycle. Here, see here how many protons are combining here. Two protons. See, one H1. This is one proton and another proton. How many protons are there here? One represent one proton here. One represent two protons. How many neutrons? No neutron is there actually. Okay. So no neutron is there. So what happens here? So one of the proton, actually on the LHS side, we have two protons and no neutrons. 1 minus 1 0, 1 minus 1 0, no neutron here. But on the RH side, what do you see? 1H2. These two lighter, two protons combine, actually two protons, these two protons combine and form, and we got a deuterium nucleus. Deuterium nucleus nothing but one proton, 2 minus 1, 1 neutron. So one proton and another neutron. But here there is no neutron, but neutron was created here. When it fuse, when two protons fuse, one of the proton will be converted into neutron. Okay, one of the proton here, this is a proton. Okay, so when the deuterium nucleus is formed, one of the proton will be converted into neutron. Okay, and so when proton converts into neutron, a positron will be created here along with neutrino, and this much of energy will be released. This is the first step that takes place in a proton cycle. This is the first step. Okay, where the two protons, actually on the LHS side we have only two protons. So but one of the proton is converting into neutron, so by ejecting positron and neutrino. This is called beta plus decay. Already we have discussed this. This is example of beta plus decay. So beta plus decay or positive beta decay. Okay, this is the first step. Okay, and see here. So actually, when two protons combine, what happens? Binding energy. So some amount of energy, some amount of mass will disappear. Correct? That will be appear in the form of energy. That is the reason for this release of energy in this in the first step. So in the second step, see here, where actually before going to discuss this reaction, what is the composition of the sun? What sun contains? What sun contains? Sun, the majority of sun, the major component of sun is hydrogen. Hydrogen, and the second component is helium. These are major components. Hydrogen is about 70, I think 70, around 73%, remaining 26% of helium will be there, around, not exact values. So here maximum uh, gas in the sun is hydrogen. Then next major component is helium and iron, etc. Okay, so this is more abundant. There are large number of hydrogen atoms are there. Okay, their pressure is, they are at a very high pressures in the sun, Actually in the sun, large number actually large number of protons, sorry, hydrogen atoms are there. And I'm telling the pressure in the sun is about 100 atmosphere, or at 100 atmosphere. The pressure is very high. Okay. And so the density is very large. It's large number of hydrogen atom. So once the deuterium is formed in the first step, what happens? Actually the core portion ఏముంటాయి, హైడ్రోజన్ ఎక్కువగా ఉంటుంది, హీలియం తక్కువగా ఉంటుంది. సో when two protons, two hydrogen, okay, actually hydrogen molecular state లో ఉండదు. Actually total gas will be in the plasma state, ionic state లో ఉంటుంది. The hydrogen is not in the molecular state, is in the plasma state, where the positive ion, nucleus and electrons are separated. Okay, so electrons are away from the positive ions. Okay, that is why here we have proton. Okay, so that is why this is a hydrogen nucleus. Two hydrogen nucleus, nothing but two protons combine to form a deuterium, and along with the deuteron, a positron, and this neutron is created. Why this positron and neutron is created? Since one of the proton will be converted into neutron, and mm, positron and neutrino are created at the time of this conversion. Okay, and he is here. What is the second process? See here, what is the first product here? 1H2. Okay, the first step. This 1H2 again combined with the one more hydrogen. Yes or no? What is the majority compound? Hydrogen ఎక్కువగా ఉంది. So whatever the deuterium was created in the first step, again combined with, will find one more proton. Like a large number of protons are there. So it will find one more proton and it fuse, these two protons fuse, okay, combine to form a helium nucleus. Okay, helium nucleus. But before going to discuss the fusion process, I want to tell one more thing here. Actually proton and proton, this is a proton, a positively charged particle, and another proton is also a positively charged particle. Actually how they fuse if together, they are positively charged particles. There exists a lot of repulsive force. Okay, there exists a repulsive force. How they are fusing against this repulsive force? Okay, so it requires external energy. Okay, if you provide, so if you want to keep two hydrogens at a this distance, at a very close distance, almost we need 400 kilo electron volts of energy in order to, if you want to fuse two protons, if you want to keep two protons at this smaller distance, we need this much of energy. We need lot of energy to ignite. Already I told, to ignite what nuclear fusion process, we need this much of energy. In order to fuse two protons, we need this much of energy. Okay, so external energy is compulsory. While in the fusion process, where the heavier nucleus, when you add one more one more neutron to heavier nucleus, what happens? Heavier nucleus, it captures the neutron, and since the binding energy increasing, so it is not it is unstable, so it splits up into lighter nuclei. But in order to ignite this fusion process, we need the input energy is very large. Okay, we have to provide large amount of energy. Why? Because they cannot fuse. Why? Because there is a repulsive force. So in order to, if you want to fuse them, so we need this much of energy. Then only the repulsive force cancel out and they start fusing. Once they come the closer separation, what happens? Nuclear forces dominates. When nuclear forces dominates, so two proton combine and produces here so deuterium. Okay, and that is the reason why, so we need uh, some input energy to ignite fusion process. Okay, now see here, what is the second process? Second process, deuterium combine with the proton and forms helium. So here also what happens? How many protons? So 2, 1 plus 1, 2 protons here, 2 protons, no problem. 1 minus 1, 0 proton here, 0 neutron here, 2 minus 1, 1 neutron here. On RHS side, 3 minus 2 protons, okay, balance, proton number is balanced. 3 minus 2, 1 proton. So on LHS side and RHS side, proton and neutron number are balanced. So no extra particle will be created like this in the first step. Okay, just only the energy will be released. Why? Because so when two protons, when individual particles combine to form a bigger nucleus, definitely binding energy increases. So that will be released in the form of energy. Okay, this is the second step. Okay, no extra particle is created here. Just we got a bigger nucleus here. So what happens in the third step? In the third step, what happens? Sun is a source of sun has a large number of hydrogen current. Here. Here helium, for example, it's second step of helium forming. Then should actually the hydrogen echo goes together. So it can form a pair like this. It may fuse with this one. Helium and hydrogen fuse couch actually. Echo only. When these fuse, what happens? What will be the bigger nucleus? Here 2 proton number is 2. Here proton number is 1. 1 plus 2 become 3. So and what about the mass number? 3 plus 1 4. So generally we have to get. For example, helium proton fuse అవుతుంది అనుకుంటే we have to get this nuclei lithium 3 4, but lithium 3 4 is not available. Lithium 3 and lithium 3 4 with the 4 number of protons with the 3 number of 3 protons and 1 neutron. There exists a lot repulsive forces. So that nucleus cannot be formed, right? Because it is not unstable. So it doesn't preserve that pair. That is why it will wait. This helium 2 3 wait for the creation of one more helium. Inkoka helium 2 3 వచ్చే ఉంట వరకు ఇది ఆగుతుంది. So one helium 2 3, another helium 2 3 created. Now it pair up with that helium 2 3 and form a helium 2 4 here. So 2 plus 2. So here helium 2 3, helium 2 3 become helium 2 4 and 2 protons are ejected. Here compare the balance this proton number on LHS and RHS. 2 plus 2 4. Here 2 plus 1 plus 1 4 balance. Number of neutrons 3 minus 1 1. 3 minus 2 1. 3 minus 2 1 2. Here neutron number 4 minus 2 2 and 1 minus 1 0 0. So neutron number is also balanced. So that is why. So what happens here? Here helium 2 3, helium 2 3 combined to form a helium 2 4 and 2 protons were ejected out, and along with the protons, so and helium 2 4, so this much of energy will be released. So this is the third step that takes place in the proton cycle. Now see the complete cycle, balance the complete cycle. So here in order to produce one helium 2 4, this has to take place one time. So to get helium 2 4, another helium 2 4, these two reactions, the first and second reactions, has to take place twice. Two helium 2 3 కావాలి. One helium 2 3 కావాలంటే 2 equations జరగాలి, 2 reactions జరగాలి. In order to get 2 helium 2 3, in order to obtain 2 helium 2 3, so we need this reaction twice. That is why I'm multiplying these two first and second reaction with 2. Okay. So and balancing all these reactions. Okay. Helium 2 3 multiplying with 2. Okay. This is the first and second reaction multiplied with 2, and it's the third reaction. Helium 2 3 and helium 2 3 combined to form helium 2 4 plus 2 protons, and this much of energy will be released. Okay. So here. So if you cancel, if you balance this equation, so here on RHS, how many protons? Here 2 1 H1, 2 1 H1 become 4 1 H1. Yes sir. This is 2 1 H1, 2 1 H1, and here 1 H1, 1 H1, this 1 H1, 2 H1 cancel, 2 H1. This will remain here. Even cancel out the second step, the second step 2 into 1h1 will be cancelled, so we'll left with the 4 1h1. If you balance this equation, you will get this one. 4 1h1 is equals to 2 helium 2 3 plus 2 protons, 2 positrons, because this takes this twice, and 2 neutrons, and this much of energy will be released. Please remember this is reaction. Okay. Right. This is a proton-proton cycle. You can see diagrammatically. See here. So this is one proton. This is another proton. So these two protons combine to form. This is deuterium. So when deuterium is formed, a neutron and sorry, a proton and sorry. See here, a positron, and neutron is affected. Similarly, one more proton and this 1H1 again combined with this 1H2 and forms helium 2 3. Okay, so this is another process. 1H1 combined to 1H2, and this 1H2 again combined with 1H1. You get another helium 2 3. This helium 2 3 combined to form a helium 2 4 plus these two particles are created. Okay, right. So this is a proton-proton cycle that takes place in the sun. Okay. Right. See some points. So this is the source of energy. This is what takes place in the sun and stars. This type of reaction takes place in the sun and stars. Okay, but this is a reaction that takes place in the sun. Okay, this is a complete cycle where 4 protons combined. What is the final expression here? 4 protons combining or fusing together and producing one bigger nuclei here. Okay, whose binding energy is large? It's stable now, and producing what amount of energy? It produces 26.7 mega electron volts of energy. Okay, so in the fission we have discussed that the nuclear energy released for fission is about in the fission it is about 0.9 MeV. But what about a energy released when 4 protons fuses? 26.7. What is energy for one proton? 26.7 by 4 will get approximately 6 mega electron volts. So in fission process, the energy released per fission is about 0.9 MeV. In fusion process, the energy released is about 6 MeV. So energy is quite large compared to fission. Next, see some points. Helium. So what we have created, what particle is created when 2 protons burn as means that when 2 protons fuse, it is producing helium. Yes, sir. So for example, after some time, all the protons are complete. What happens? So all protons are converting into helium. So initially helium is synthesized. Okay, helium can be synthesized in the interior of the star and sun. Initially helium created. So once all the hydrogen is completed, what happens? This helium and helium combine and produces carbon. And next carbon combine and produces further bigger nuclei. And this process continues. Okay, so the star begin to collapse. Here, see, this is the second point. So here, not only helium is created, but the heavier particles also synthesized in the nuclear fusion reactions. As the hydrogen in the core depleted and becomes helium, the core, the central part of this star and sun become cool. Yes or no? Once the fuel is completed, once hydrogen is completed, the star begin to collapse. Then what happens to the star? The star begin to collapse. So due to its gravity, so when it collapses, once again the density increases. Once again the temperature increases. This temperature goes to very high. So at this temperature, heavier particle fuses. So for example, in terms of Japan, so in order to fuse, so here when 2 protons, if you want to fuse one H1 and one H1, what is the temperature required? So 10 power of 7 means, so what is the energy required? 400 kilo electron volts. So already I told you it requires 400 kilo electron volts, and that will provide this much of energy. Okay, so what is happening here? What is happening? So here, sorry, here, as the hydrogen in the, sorry, the star begins to collapse under its own gravity, which increases the temperature. No, temperature increases to 10 power of 8 now. Okay, so at this higher temperature, bigger particles start fusing, higher particle. So particle with elements with more mass starts fusing. Okay, so here, helium and helium fuse together to form a carbon like this. This kind of process generates through fusion higher and higher mass number elements. Okay. Higher elements can be synthesized. Okay, are produced. Okay, but the elements are more massive. But the elements more massive than the iron. Iron has more binding energy. After that, binding energy decreases. So after that, so no energy will be released. That is why that process will not take place. So why they are fusing? They want to increase their binding energy. So when the binding energy increases, more energy will be released. Okay, so and this process starts once we got iron like elements, so the process stops. Okay, we cannot synthesize elements which are more massive than iron, right? Because their binding energy is small, so that process will not take place. This is about the nuclear fusion. Some points regarding nuclear fusion. Okay, next controlled thermonuclear fusion. Okay, controlled thermonuclear fusion. And then we have discussed this word. You heard about a controlled fission reaction. Where controlled fission reaction takes place in nuclear reactors. Okay, if you are able to control this nuclear fusion process, we can also produce controlled fusion reactors, not fission reactor, fusion reactors. Okay, so and in order to ignite, I told that in order to ignite fusion process, okay, we need this much of energy, this much of temperature, 10 power of 7, 8 to 10 kelvins of temperature. But at this temperature, actually, all the fuel is a mixture of ions, plasma state only. Okay, at higher temperatures, there is no molecular state, atomic state only. So all the matter is in the plasma state. No, there is no bonding between the positive and negative ions, positive charge and electrons. So, but there is no. So, but if you want, but I want to construct a nuclear fusion reactor. So, but what is the problem? What is the difficulty? So, how can you hold that much of temperature? So, what is the container? So that can withstand such high temperatures. We cannot maintain a temperature in any in a region. So if you cannot maintain any material whose melting point is less than this 10 power of 8 only. So no material is there that can withstand this much of temperature. That is why it is difficult. Future we can expect nuclear. Let us hope there will be nuclear fusion reactors that produces large amount of energy and which is very safe. No no harmful products are produced. So see some differences between nuclear fission and fusion. So neutrons are required. So in order to ignite the nuclear fission process, what we are adding? So how the nuclear fission takes place when neutron is bombarded. This is a neutron. So it is bombarding uranium-92. This is uranium-92-235, which is a fissile material. So it becomes uranium-92-236, which is unstable. Later it splits up into different particles, both barium and krypton, and large amount of energy will be released. So in order to start fission process, we need neutrons, thermal neutrons particularly. And nuclear fusion, in order to ignite a fusion process, we need protons. Okay, so here in second point here, it is impossible it is sorry, it is this nuclear fission process is possible at normal temperatures and pressures. But so what I told, what is the pressure of gas in the sun is about 200 atmospheres. So what is the normal temperature and pressure? What is the normal pressure? 1 atmosphere. But where the nuclear fission takes place at 200 atmospheres, very large, huge pressures ఉన్నాయి అక్కడ. So then only fusion takes place. Okay. Then density, pressure, and temperatures are very high. Okay. So an energy released for nucleons in the nuclear fusion, I already told, 0.9 MeV. When one uranium breaks down, so it produces 0.9 MeV per nucleon. So this energy released per nucleon is about, in the fusion process, it about 0.6 MeV. Okay, so it is big, quite large as compared to fission. And so already I told this point also. In this process, 0.09% of mass will be converted into energy, and nuclear fusion process, around 0.7% of mass will be converted into energy. So more energy will be liberated here. So, but so even though it is producing, even though nuclear fusions are producing here, so sorry, harmful nuclear fission. So here harmful products, elements are produced here, but in nuclear fission process there are no harmful products. So that is why it is much safer. But so it is alright. No, at present we don't have any nuclear fusion reactors. In future we let us hope so there will be a fusion reactor. Okay, which research is going on. Okay, so this is about today's class, and this chapter is completed. Okay, so you can ask doubts in the classrooms. Okay, right. And thank you all. Thank you.